Okay, hi guys. So let's talk about potential energy. Okay, so the first thing we want to talk about is just this idea of an interaction and how we're choosing our system. Um, so, right, we're looking at two particles, A and B, right, and they interact with each other. Now, that can be a variety of different ways of interacting. Usually, we're going to build our intuition mostly based on gravity, so that might help. Um, and so in this case, it would be like the object and the earth. All right. And we're used to thinking about this doing external work on the object, right? So when we calculate that, we're saying, W equals, that mg times d, which we've done a couple times. Okay. Or you can think about the whole thing as an interaction, the whole thing as a system. And when you do that, you get a very useful concept called potential energy. Okay. Um, so actually, you know what? I think, yeah. So so you can look at these later, but I feel like maybe I just want to riff on my iPad. Boom. New recording. Oh, screen recording. I just did something funky. Sorry. Okay. So, I'm not sure why this is not showing now. Okay. I apologize. But, oh, it's because it's not recognizing that it's plugged in. Okay. Anyway, I'll just talk to you while this thing is thinking about how to do this. But the concept of potential energy is, as I was saying near the end of class last time, is this really great way of really quantifying a field. And we're going to talk way more about fields later. So gravity is a field, and the electrostatic field is another very important one. And we are going to talk a lot about using our intuition for gravity when we start talking about electrostatics next semester. So I'll try to bring those up as appropriate. So things I need to talk to you about: conservative versus non-conservative. Okay. So gravity, electrostatics, spring force. These are all examples of conservative forces. Non-conservative forces are things like tension, things like applied forces, normal force, friction. Friction is, of course, a big one. And that's usually because a lot of times these don't do work just because of the way that they're structured. Like if you've got a normal force, but it's actually going this way, you're going to get no work. So that tends to happen, like in a centripetal situation, like Tarzan, right? This tension does no work because the displacement is perpendicular to the force. But friction is one that we use a lot when we think about non-conservative forces. Okay, so when we're thinking about conservative forces, what's really important is that there is a potential energy associated with each conservative force. Okay, potential. Sometimes I write PE, sometimes I write U. So you should be used to sort of going back and forth. Okay, so what's the difference? Definitely the fact that there's potential energy associated with the conservative force is important. Another thing is if I go from point A to point B, and I do this, or I do this, or I do this, okay? The work done by a conservative force, oh my gosh, that says conservative, is path independent. So, and this really goes hand in hand with this idea that the work done by a conservative force is negative of the change in potential energy, because the idea is that I can define a potential energy when it's here, and I can define a potential energy when it's here, and right, I've got UB minus UA. And the point is that you have no idea how it got from A to B. And that's the glory here, is that it's really just this difference of the two. Contrast that to, this thing, I don't know, it's moving and it slows down because of friction, right? If it goes further, there's more work, right? So work by non-conservative depends on path. Okay? All right. Boom. So let's actually prove, sorry. The thing is, I'm not going to go back and re-record this. I only got a little bit of time. So let's just muscle through. All right. I just sort of threw at you, and because you knew it before, that U for gravity is mgh. But let's actually do it. Let's actually show that. Okay, so let's take the situation of an object going down, right, falling. Okay, it starts with this initial y, and it ends with this final y. The force that it feels is gravity. Okay, and I'm going to calculate the work done by gravity during this experience, right? So it's going to fall. So work is integral of F dot, and I'm going to write dy here, right? That shouldn't bother you too much, hopefully. It's just a distance, and it's more natural for us in this gravity thing to think about the y distance. And so I'm going to do that integral from y sub I. Oh, I'm running out of room, sorry. That says yf, y sub f. Okay. And then this was the work done by gravity, so this is the force due to gravity. All right. So yi to yf, the gravity and the distance everywhere along this path is going to be cosine of 0, right? So cosine of 0 is 1 for that dot product. So my FG is just mg, right? And my dy, each one of these little dy's all the way down, is just dy, and then there's a cosine of 0, which is 1. Okay? Pretty. So obviously, mg is a constant, it can be pulled out. And so I have yi to yf of dy. So that's mg. The integral of dy is just y. And if we're going to evaluate at the top one and then evaluate and then subtract the evaluating at the bottom one, you get that. So if I said that the magnitude of this distance that it fell is h, then the work due to gravity is what? Negative mgh. Why? Because yf is less than yi. So yf minus yi is negative. And if I'm going to write h as that magnitude, that just distance, then I get this negative. Okay? So what you get here is by doing this process, you're actually defining what that potential energy is. Okay? So, so I have more room. So now I can define my potential energy associated with gravity as mgh, right? But again, that h, you have to know where you're measuring that from, right? And just the value of potential energy actually has no physical meaning. The only physical thing that happens with potential energy is delta, okay, is the change in potential energy. And so if we take this and we say, all right, it's mgh final minus mgh initial, that's just literally what delta is if I've defined this u that way. And so that's mg delta h, right? And in this case, our delta h was less than 0, right? So that's how I got this negative mgh. So, Ruby. So, hold on. Yeah, okay, that's fine. So the work done by gravity is this. Now I'm feeling uncomfortable about what just happened up here. I'm not entirely sure I got all my negative signs right over here, but this is true that we just define it this way, and this is true. So if I messed up something over here, then don't worry about it. But we can absolutely, oh no, my Apple battery is low. My Apple Pencil battery is low. Okay, so that is important. And apparently I have to go to AT in 10 minutes. So here is, so I'm not actually done with today's lecture, but I think I'm just going to do this in 2 bits. But let me finish this part and then I'll do another part later when I have time. Intuition builder, all right? Things want to lower their potential energy, right? I hold up the ball, what does it want to do? Right? It wants to lower its potential energy. This is super important, okay? So when things want to do, oh, sorry. When things do what they want to, the work done by that conservative force is positive and delta U is negative, right? Things want to decrease their potential energy. And because of that relationship with the negative sign, that means that the work is positive, okay? And literally almost every single work problem, I ignore the sign, I calculate it, and then at the end, I use this intuition builder to figure out what the appropriate sign is. That's a really, really good trick. All right, I'm going to stop this recording and then I will pick back up later.